You okay? There you go. All right, give me just a minute to finish running water. Give them that. Don't forget. That's not that great. And now I'm here. Hello. This is great. This is amazing. I see no problem here. Like everything. It's a great spot. I'm wondering. Jeez. I can't even remember. I can't. I'm I don't know which one I was. Oh, so. It's not. I'm just glad. Fun though, watching all the colors on.
First thing people suggest, what is time zone? What? No, I didn't look at that. No way. There's no way. Don't worry about it. No.
That's great. And we're still fun.
Dude.
Y'all okay back there?
No.
Losing it?
Yes.
Oh, God, what happened?
Oh.
It's pretty. Looks like it's play or something, but it's not. You're like. Yes. That's gonna be.
Yeah.
Right on. Skippity. Yes. Yeah, I'm like crazy. Do it. But like.
No.
So it's funny.
Well, maybe.
Well, maybe. What do you mean? Oh my god.
Oh, I said
What is it? I-
Oh, you I used
saw that
to.
video.
I just know what we're. How did you know what it means? Without looking it up.
I like Pokemon. We thought I knew what the Pokemon things are.
Oh,
so then.
I see that.
Let me read you the definition. Oh, you know. It was my last thing, guys. Don't read it out, but. Why do you still not there?
Wait, bro.
You know, it's a no.
We're gonna get.
And, but yeah.
I shot it's pretty higher on this side.
On the kids.
Thank you, well. I'm waiting to shut it.
You will be happier. 10 minutes. Be happy.
Sorry for the delay, but I don't ever want anybody to accidentally spill acids or bases on themselves, so if I get a chance to get liquids and stuff off the counter, I do. And the burettes take a while, as you can imagine. All right, so we are moving on to acids and bases, specifically in solutions and physical properties of dissolving them. Are we with it back there? Uh-oh.
We are good.
What happened?
We are good. It's good. like-
Y'all are crazy. All right, are we good? We're good? We're actually good? We're all paying attention? All right, let's roll here. All right, let's see. Acids and bases in solution. So acids conduct what very well? Caitlin. Yes, Caitlin, very well. And they react with many what?
Metals.
Metals, okay. And acids generate what kind of ion, Yusuf? No, hydronium is what we're looking for. So acids are proton donators, right? They donate those H plus, but they can generate H3O plus. And the reason they can generate them is because a strong acid is going to dissociate or ionize in an aqueous solution. And when it does that, it's going to produce these little H plus, right? That it is willing to donate. And some of them are going to attach themselves to the water molecules. And a strong acid is going to lose one proton, which is captured by a water molecule, and it's going to create these little hydronium, H3O plus, but they still have that positive charge, right? And a weak acid is one that does not fully ionize when it's dissolved in water. Were our acids today strong or weak acids? Do we know? They were diluted, but they're strong acids. And our base was actually a very strong base, but they were heavily diluted. We had like 0.1 molar and 0.3 molar were our varieties of different, I think 0.1 for both the, was it 0.1 for both the hydrochloric and the sulfuric, and then the sodium hydroxide was 0.3. So yeah. Now, just so you know, when you go to buy chemicals, in case you're curious, you can buy chemicals at various molarities already in solution. So both of our acids came in little white bottles back there on the counter. They were 1 liter of each. They were already in solution, but I did not have any 0.3 molar sodium hydroxide. So I had to make that. So how do you make that? You have to know about your molarity and your volume, and you have to do the little calculations, or you can get apps. There are apps for that. There's an app for that one that I use sometimes called Lab Hacks. It's a great app, but it'll help you, like here's your mass molarity calculator. So all you need to know is your molecular weight, which is easy, right? Your desired final volume and your desired concentration, and you can do your concentration in everything from molarity to mass, nanomolar, and it'll let you tell you exactly how much to add. So that's really nice too. So yes, it's good to know how to do calculations, but technology is fun. Okay, what do bases generate? What kind of ions, Jordan? Hydroxide ions, which is OH negative, right? So bases are generating your negative ions and acids are donating your positive ions. So a strong base, somebody have a definition for a strong base? What you get, Colin?
I think that ionizing completely involved.
Yes, completely disassociates in an aqueous solution. So they ionize in water to yield one or more hydroxide ion per molecule of base. That's what makes it strong. And then a weak base is going to, Caitlin?
Base that releases two hydroxide ions.
Right, it's only going to partly dissociate in the water. Now we talked about how acids and bases are gonna, okay, what are we doing? All right, acids and bases, your acids are gonna donate your H plus ions, your bases are gonna accept them, but they're gonna produce your OH negative ions. If you put an H plus and an OH negative together, what do you get? H plus and OH negative together. Think about it. An H plus and an OH negative, if they combine, what do you get? Yeah. Neutral what? What is the compound? H plus and an OH negative. Listen, you have an H plus and an OH negative. When they combine, your charges have canceled out. Yes, it's neutral. What is it, Caden? You're gonna get, you have an H and an H and an O. What are you gonna get?
Neutral H2O.
Neutral H2O. You're gonna get H2O. Remember we said acids and bases, when they neutralize, they produce water and salt. Your water comes from that H and OH combining. That's where you get your water from. Your salt comes from whatever other components were part of the acid or the base. So let's remember, acids neutralize what? Bases. Bases neutralize acids. Acids can dissolve some metals and they're kind of sticky, whereas bases are slippery. Acids turn blue litmus paper red. Bases turn red litmus paper blue. Acids taste how? Sour. Bases taste bitter. A molecule or other entity that can donate what? Donate a proton or accept an electron. And then a base is a molecule or other entity that can accept a proton and donate an electron pair in reaction. So you've got your acids donating protons, your bases donating electron pairs, your acids accepting electron pairs, your bases accepting protons, right? Acids have a pH of what compared to 7? Less than. Bases have a pH of more than or greater than, higher than. A chemical substance, acid here, a chemical substance, usually a liquid, which contains what and can react to a base to form salts. What is in them that is causing the reaction? That hydrogen, that H plus ion, right? Yeah. A chemical substance, which what's in a base? Not hydrogen, but hydroxide. Okay, what was the name of the base you used today?
Sodium hydroxide.
Sodium hydroxide. So you knew it was a base before you didn't have to do anything with it. You knew it was a base. What were your acids? Hydrochloric acid, and then we call it sulfuric, but really it's hydrosulfuric acid because it's H2SO4. We just shortcut it and call it sulfuric. It's really hydrosulfuric. And then your hydrochloric acid. They both had an H, right? Just an H. And then your NaOH has your hydroxide, so you know it's your base. So your acids have your H plus, your bases have your OH negative. Anything that has hydroxide in the name, you know is going to be a base, right? All right. Acids and bases, says Ted Ed. And I think, okay, is our commercial going to be for Georgia Natural Gas or I want to be a doctor? Who votes for I want to be a doctor? Who votes for natural gas? All right, let's see what we get. Or it's Harbor Freight. Ah, natural gas. Some of y'all win. Eternal glory. That's all anybody wins with me. Eternal glory. I don't have a big enough budget. I have to keep replacing Burette.
They're used to make food, soaps and detergents, fertilizers, explosives, dyes, plastics, pesticides. Our stomachs are very acidic. Our blood is slightly basic. Our proteins are made up of amino acid. And the letters in our genetic code, those A's, T's, C's, and G's, are all bases. You were probably taught how acids and bases behave on the molecular level. You were probably never taught that a long time ago, like ancient Greek ago, before anyone knew about atoms or molecules.
TJ, can you sit up for me, honey? Thank you.
Acids tasted sour and corroded metal. Bases felt slippery and could somehow counteract acids. When molecules dissolve in water interact, they're exchanging two main currencies with their surroundings.
What's acetic acid? Anybody know? What is it? Vinegar. Yep.
Also known as hydrogen ion. Electron.
Vinegar.
Depending on how a molecule is composed or picked, it may be willing to donate or accept either protons or electrons with some other community member. And some molecules are far more aggressive than others when it comes to donating or accepting either currency. Remember that protons are positively charged and electrons are negatively charged. So if a molecule is willing to give up a proton, that's not too different from it being willing to accept an electron. Either way, it's becoming more negatively charged. Other molecules are willing to accept a proton or give up an electron. These are becoming more positively charged. Some substances are so aggressive about donating their protons that when they get a chance, all of the molecules in a sample will dump a proton, sometimes more than one, to the surrounding water molecules. We call these strong acids. Meanwhile, some compounds are so ready to accept a proton that they won't wait around. They'll just rip one off water, which usually has two protons, but is generous enough to hang out with just one. We call these strong bases. Other acids and bases are not so strong. They may donate just a few of their protons to water, or accept just a few protons from water, but most of their molecules stay exactly the same. If left alone in water, they'll reach some equilibrium point, where maybe only 1 out of 100 or 1 out of 10,000 of their molecules have exchanged currency with water. As you might guess, we label these acids and bases weak, but in the common sense of the word, they're not weak. The vinegar in your salad dressing that you can smell from across the room, that is a weak acid. The ammonia you spray on glass for a streak-free shine, that is a weak base. So it doesn't take much to be an active player in the chemical blend. Most acid-base chemistry takes place in water, which can act as either an acid or a base, accepting deposits and enabling withdrawals like a 24-hour molecular ATM. And a proton deposit customer, that's an acid, and a proton withdrawal customer, base, shop at the same time. Their net effect on water's account may cancel out, and we call this neutralization. Now, certain molecules can behave as acids or bases without water, but that's another story. Let's end by saluting water as the resilient and fair banker for acids and bases. It's always open for business, doesn't charge interest, and will never foreclose on your molecules, which is more than I can say. Wah.
Okay. So there are different ways to describe acids and bases. We have Arrhenius theory, and you've probably read yet Bronsted-Lowry. So Arrhenius theory, this is Svante Arrhenius. He's a Swedish chemist, and he proposed the first, you good? The first definition of acids and bases. Substances A and B became known as acids and bases. So according to the Arrhenius model, acids are substances that dissociate in water to produce H+ ions, hydrogen ions, and bases are substances that dissociate in water to produce hydroxide ions. True? We all agree? Okay, so that's one way to describe them. So here you have NaOH, which you used in lab today, right? And it will dissociate into NH+ and OH negative. And because you have an OH negative, it's a base. Your hydrochloric acid will dissociate into your H plus and your Cl negative, and because that H plus is present, you have an acid. If you neutralize sodium hydroxide with hydrochloric acid like you did today, what two substances are you going to produce? What are your products going to be if your reactants are sodium hydroxide and hydrochloric acid? Jordan? What salt specifically? Very good. Sodium chloride and water is what you'll get. Very good. Exactly right. So you did that today when you neutralized. There was a moment there, right, when it shifted from acidic to basic, and that's what you would have had. All right, now we have Bronsted-Lowry classification. This is another way to describe acids and bases. So Bronsted-Lowry classification is concerned with protons. So Bronsted-Lowry acids donate what, Caitlin?
Proton.
Protons, or that little H plus. Bronsted-Lowry acids, a donor proton, they can call it sometimes a PD, proton donor, okay? It's a proton donor. Bronsted-Lowry bases accept what? Oh, protons. There we go again, because Bronsted-Lowry is concerned with what? Protons. That's what they're concerned with. So they are proton acceptors. Or I guess you could say it was a PA if you wanted to, but sometimes you'll hear them referred to as proton donors, proton acceptors, because all Bronsted-Lowry cares about is whether they accept or donate protons, whereas Arrhenius was more about hydrogen ions versus hydroxide, right? Hydroxide is present in bases, hydrogen ions are present in acids. Okay, so acids and bases, what do you have for that one, Caitlin? Conjugate. Yep. Okay. So a conjugate acids and bases. What's a conjugate acid? What you get? Yeah, an acid base in an acid base reaction in the Bronsted-Lowry one. This is what we're dealing with protons. A conjugate acid is the species formed after the base accepts the protons. The base accepts the proton. Whatever's left is your conjugate acid, and then your conjugate base is going to be formed when? How? Caitlin?
Forms when an acid loses a proton.
There you go. Formed in the acid-base reaction, and it's the species formed after the acid donates its proton, right? So if you think back to that sodium chloride, it's going to be that sodium and that chloride ion that are left, or that sodium ion that's going to be left with that conjugate base, sorry, and the chloride ion up here in this case. So species are both acids and bases. What are these, Caitlin? Yeah, fun word. Amphoteric. Okay, so somebody tell me amphoteric, Colin?
Describes a substance such as water that has properties of acid and properties of a base.
Right. Okay, water's going. So a compound, especially a metal oxide or hydroxide, that's able to react both as a base and an acid. Water is a good example too, both as a base and as an acid. All right, so Bronsted-Lowry acids donate this H plus, which we name hydrogen, proton, yep. And then the Bronsted-Lowry bases accept protons again, right? They accept protons. And then this would be your Arrhenius theory, H plus, OH negative. All right, so here are dudes, Johann Bronsted and Thomas Lowry. When you see a name like this with that O through it, you know they're from where probably? Somewhere Nordic. Yeah, Sweden, Denmark. They're the guys that do the little, you ever been down to IKEA? There you go. Like half the stuff in IKEA has that little, bless you. Yep, there you go. So Johann Bronsted and Thomas Lowry revised Arrhenius acid-base theory to include this behavior, and they have defined acids and bases as following. An acid, that should be an arrow right there. An acid is a hydrogen-containing species that donates a proton. A base is any substance that accepts a proton. So in this example here, what's the acid and what's the base? What's the acid? This is the acid. And what accepted the proton? Look over here. Where did that H go? H3O. There you go. It went right here. That's it. And what is that? H3O plus. That's hydronium. That's hydronium, and water will disassociate all on its own and form hydrogen and hydroxide. And those free hydrogens will attach to existing H2O molecules and produce that H3O plus, and you get hydronium. So in reality, the reaction of hydrochloric acid with water is an equilibrium that occurs in both directions. Although in the case of this equilibrium, it lies pretty far to the right, this side, right? And for the reverse reaction, that chloride ion behaves as a Bronsted base. See, this guy, if you're going in reverse, it's going to be your base. And the H3O is going to be your acid, because this is going to accept a proton from right there. Right? Okay, so Cl negative, that chloride ion is your conjugate base of HCl. Bronsted acids and bases always exist as conjugate acid-base pairs. Their formulas differ only by one proton. So it's the acid-base pairs. They exist in conjugate pairs. All right. So here's a little more on Bronsted-Lowry theory with some graphics that might help.
So excited about.
Oh, it's this time we got med school. Last time we got Georgia Natural Gas. This time we got go to med school. Yay. And insurance. Yes, yes. All right, here we go.
The Arrhenius theory of acids and bases defines an acid as a substance that releases protons in solution, and a base as a substance that releases hydroxide ions in solution. We know that ammonia can act as a base and exhibits alkaline properties, but contains no hydroxide ions. How is this possible? In this lesson, we will learn about the Bronsted-Lowry theory of acids and bases, which fills in the gaps in the Arrhenius theory. You have learned that acids are substances with a pH lower than 7. We can test for acids using universal indicator solution or paper, which turns red or orange, all depending on the strength of the acid. Blue litmus paper also turns red in the presence of an acid. An example of an acid that you are likely familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. Hydrogen chloride will dissociate to give a proton and a chloride ion. The proton is not just released, but it is transferred to another substance. For our example, water accepts the proton to form a hydronium ion. A hydronium ion is also known as an oxonium ion. The Bronsted-Lowry acid is a substance that releases or donates protons in solution. In our case, hydrogen chloride. A Bronsted-Lowry base is a substance that accepts protons in solutions. In our case, water. Notice that the definition of a Bronsted-Lowry acid or base is not a function of pH. So an acid-base reaction, according to the Bronsted-Lowry theory, involves the transfer of a proton from one substance to another.
Y'all paying attention?
In the introduction, we mentioned that ammonia acts as a base, even though it does not release hydroxide ions, stipulated in the Arrhenius theory. When ammonia dissolves in water, it accepts a proton from water. Notice that this reaction also involves a proton transfer. Can you figure out which substance is acting as an acid in this example? Which is acting as a base? Please pause the lesson to think about this and resume when you are ready.
I am gonna pause it. So which of these two is acting as the acid and which two is the base, James? Water's the acid and ammonia is the base. Anybody disagree? Okay.
In this example, water acts as a Bronsted-Lowry acid because it releases a proton. Ammonia acts as a Bronsted-Lowry base because it accepts a proton. So a base, according to the Bronsted-Lowry theory, does not need to have a pH greater than 7 or turn red litmus paper blue, or turn universal indicator solution or paper blue or purple. The only requirement is that it is able to accept protons. Have you noticed that water acted as a base in our first example, but as an acid in the second example? Substances that can act as either an acid or a base are amphoteric. In conclusion, according to the Bronsted-Lowry theory, an acid is a substance that dissociates to release or donate protons. A Bronsted-Lowry base is a substance that accepts protons. Therefore, an acid-base reaction, according to this theory, involves the transfer of a proton.
So why was it important to revise the Arrhenius theory? What was the Arrhenius theory missing? Arrhenius said that acids produce hydrogen ions, bases produce hydroxide ions. What was missing from that makes it an incomplete theory on acids and bases? So Bronsted-Lowry focused on protons, not the neutral. Not all bases are gonna have that hydroxide. Now, if it has a hydroxide, it's a base, but not all bases have the hydroxide. Some substances, ammonia was their example, which is NH3, does not have a hydroxide, but it can accept a proton, in which case it behaves as a base. Therefore, Arrhenius theory was not complete, and Bronsted-Lowry revised it and said, okay, yeah, that's all true, but there are some substances out there that behave as bases that don't have that hydroxide ion as part of the compound, the formula. So if they can accept the proton, they're a base. If they can donate the proton, they're an acid. Does that make sense? And then you have amphoteric species, which are what? They behave as both. They can behave as both acids or bases, depending upon what they're paired with, right? So here's a little more about conjugate acids, bases, conjugate pairs. So hydrochloric acid, and what's this? We just saw it. We just learned what this is. NH3 is ammonia. Okay. Now, when you put them together, your conjugate pair is right here. This is where your proton got added on this side. But when you add, you see that you still have the NH and the NH. This is that other H, right? This H popped over here. So those are your conjugate pairs. And you can see it right here too. HCO3 negative, your acid. And then right here, you've got water. It's going to act as your base. And on this side, you're going to get hydronium and CO3, 2 negative. And here are your conjugate pairs, HCO, HO, because it has to do with where your proton goes. So whenever an acid donates a proton, the acid changes into a base. And whenever a base accepts a proton, an acid is formed. An acid and base, which differ only by the presence or absence of a proton, are called your conjugate acid-base pair. Okay, so let's talk a little bit about pH. We had pH indicators going in lab today, right? And before lab in our demos. But what's pH? So first we have to talk about water and the fact that it self-ionizes. So a minute ago I said that water will automatically dissociate and form hydroxide and hydrogen ions, right? So now you have a basic species and an acidic species, right? But this little guy is able to pop on to an existing water molecule. And when that happens, you get hydronium.
Can anything besides water be neutral and add acid and base at the same time?
Say it again.
Can anything besides water
Be amphoteric? Yes, there are other amphoteric substances, like let's say metal oxides and a few others can behave amphoterically. So yeah, but water is a great example because you can see because it's very basic. It's a simple molecule, right? So you can see what happens. This little guy pops off and he goes over here and now you have hydronium, which is positive. So water can undergo auto-ionization. Auto means what? What's auto mean? A-U-T-O, auto. Here we go with Greek and Latin again. What's an autobiography? Self. There you go. Self-ionization. So the equilibrium constant for water, which we're going to talk about equilibrium constants in a minute, is 10 to the negative 14 at 25 degrees Celsius. So basically, in a neutral solution, you have your H3O plus, and you're going to have some hydroxides floating around. In an acidic solution, you got some there's all sorts of things that are happening in just like a glass of water. There are protons moving around, and there are water molecules dissociating into ions. You've got hydronium forming. But how often does it happen? We'll talk about how often it happens in a minute. Oh, here it is. That's this slide. One in how many water molecules do you think is going to auto-ionize? One in how many? 1 in 100?
1 in 1.
1 out of 1? Everyone?
1 in 2.
1 in 10?
1 in 2.
1 in 2? All of them? You got a guess, Rylan?
Billion?
1 out of a billion? Okay, so it's 1 out of. You're halfway there. There you go. 500 million. 500 million. So 1 in every 500 million water molecules is going to auto-ionize. So that sounds like not very many, but if you think about how many water molecules are in a glass of water, you know, there's a fair number in there that are popping off and auto-ionizing. So again, when they auto-ionize, you're going to end up with the following. You're going to end up with H3O plus, which is your hydronium, and then your OH negative, right? So this yields a hydronium ion, this dude right here, concentration of 1 times 10 to the negative 7 moles of hydronium per liter. So 1 times 10 to the negative 7 moles of hydronium per liter. James. Nothing. So this is why when you looked at the pH scale from 0 to 7, were you like, and then 14 on the opposite side, where you're like, why is that? 14 on one end, like that is random, right? It's not random. What's that number? -7. And there's this thing called a log. We're going to talk about this in a minute. Logarithm. If you do the math, 7, there's where your 7 comes from. Okay, so waters, we're going to come back to it. Water is amphoteric. So substances that can act as proton donors, acids, or proton acceptors, bases, depending on what substances are present. So in this case, and in this case, hydrochloric acid with water, your water's a base. Ammonia with water, your water's an acid. Because you can see where your conjugate parts go. Conjugate acid, conjugate base, conjugate acid, conjugate base. So she's going to explain amphoteric to you. She looks like it, doesn't she? She's going to explain it just a little. I mean, I've already explained it. She's going to explain it again.
Fearless.
Oh.
I had to consider
Oh,
this.
I don't know what that's about.
Kind of a
Sad.
cool word. We're going to talk about amphoteric species. Before I let the cat out of the bag, I want to show it to you, and then you'll really understand it. Just a reminder, an acid donates a hydrogen, a base accepts hydrogen. So I wrote my example in this first equation up here. The nitric acid that is going to donate the hydrogen, water is the base, is going to accept the hydrogen. So we come over here, you can see, yep, sure enough, nitric acid lost that hydrogen, becomes nitrate, that's the conjugate base. And the water accepted the hydrogen, so that becomes a conjugate acid. As you look in the reverse direction, you can see the base that's going to accept a hydrogen, and this acid is going to donate the hydrogen. It's important to have these labeled. I've done the rest of these, which is some shorthand to save some time. A is acid. Let me put this here. A is for acid, B is for base, CB is conjugate base, and Ca is our conjugate acid. Okay, so let's look at the second reaction. The ammonia is the base, is going to accept a hydrogen. Yep, gains a hydrogen. The water is the acid, is going to donate a hydrogen. So I have 1 less hydrogen now. If we turn around here, go in the reverse direction, yep, sure enough, this ammonium is going to donate the hydrogen, we give the hydrogen back to the water, and the hydroxide is going to accept that hydrogen, so that's your conjugate base. Now, just looking at these two, I want you to zero in on water. What do you notice? Here, water is a base, and here, water is an acid. Water can act as both an acid and a base. Books and books and books have been written about water. Water is amazing on so many different levels.
Books on
This
water.
is one of them. Pretty cool. Water is amphoteric. What do you think that means? It's both an acid and a base. So let's write that down. Amphoteric simply means
Amphoteric.
a species is both an acid and a base. And I could say it acts as both an acid or a base. It depends on what it's with. It depends on what it's with. If it acts like an acid or a base. So those two right there, there's your acid, there's your base, same species, is amphoteric. Those are amphoteric. Let me give you another example of an amphoteric species.
So here's your
Okay,
not water.
So I have my sulfuric acid. Now this is a diprotic reaction, and you'll recall that when you have more than one hydrogen, the hydrogens will always lose one at a time. They each have their own reaction, their own step. If you have questions on that, under acid base, the playlist, watch my polyprotic video. Okay,
She got all the videos, this lady.
my main focus on amphoteric for this. So we have the sulfuric acid plus the water, there's your acid going to donate a hydrogen, you can see it. The base is water going to accept a hydrogen. So then I have what's called hydrogen sulfate plus hydronium. Okay, so we lost one hydrogen. Now this species right here is going to lose a second hydrogen. So this does its own separate new chemical reaction. So this species, the hydrogen sulfate, is going to react with the water that's in that solution in the beaker. And it's going to donate a hydrogen. It becomes sulfate ion. And the water, of course, is the base. It accepts the hydrogen to become hydronium. So look at those two reactions. Can you see
The hydrogen
an
sulfate.
amphoteric species? Something that is both an acid and a base. I bet you found it right here.
Yeah, found it.
Hydrogen sulfate here.
So
notice
there's
it's
your
going in the
example,
reverse direction,
Colin, that you
but
asked
it's
about.
going to
right there.
accept a hydrogen. That's a base. And then here, when it does its own separate reaction, it's an acid, acts like an acid. So when you have polyprotic reactions, they're going to have species that will be amphoteric. That they act as either a base or an acid. They could donate that hydrogen or they could accept the hydrogen. Donate acid, accept would be the base.
All right, so she is cool. She's got, her channel's great. So if we talk about what does pH mean? All right, now we're switching gears to pH. What does pH mean? So if we're talking about pH and acidity, neutral is what? Jordan? Yes, exhibiting neither acid nor alkaline qualities. And on the pH scale, we give neutral the number of what? Drew? 7, yep. Okay, so pH is a measure of hydrogen ion concentration, a measure of the acidity or alkalinity of the solution. The pH scale usually ranges from 0 to 14. And we calculate pH from, Colin? H3O+. Okay, now. Remember when I said that pH scale has a meaning? Right? All right, now, I asked this type of question, what does pH mean? This was the type of question. And I actually asked my 7th grade pre-algebra teacher, Ms. Prisparowski. She was a student teacher, Ms. Prisparowski. I was telling this story in the car the other day on the way to gymnastics. I asked her a question, and my question was, well, what's pi? And she was like 3.14. And I'm like, well, thank you, but what is pi? Like, you can't just like pick a number out of thin air and then it magically works. That's not how things work. It has to mean something. she couldn't answer what is pi, and she got so frustrated that she was reduced to slobbering tears, and I felt like dirt because I did not mean to make the teacher cry, but I just wanted to know where the number came from. This is the same kind of thing. I've never gotten a really great answer. There's an answer, but I'm not good at explaining it. But she did not explain it that day. I think she thought I was picking on her, and I've never picked on a teacher in my life. But the same thing as pH. What does that mean? Well, we talked about, we can see where the numbers come from now, right? We explained how we got to the numbers 7 or whatever. But here's the fun thing. It's still disputed. What does pH mean? Okay, so this dude is Sorensen, S.P.L. Sorensen. He's a Danish fellow, okay? So he's the one who came up with the term pH, but he never explained why. Thank you. That's great. For all of us that want to know what it means, you don't tell. So he described a way of measuring it using potential, which starts with a P, right? Differences. And it represents the power, which also starts with P, of 10. Remember we saw that log and the exponents? Okay. In the concentration of hydrogen ions. So all of those words, power, potential, they both start with P in German, Danish, French. Fun. We don't know what he's doing. So the all languages that he spoke and published in, and he was in the Carlsberg laboratory at the time, which was French speaking, though German at the time was the dominant language for scientific publishing, and he was Danish. So what does this mean? We don't know, because he also used Q in kind of the same way, elsewhere in the same paper. So the P could be puissance, which is French, or it could be the German potens, or it could be Danish potens, which all mean potential, or power, sorry, they all mean power, or it could mean potential. We don't know what he meant. He might have just randomly labeled one solution P, and then the other arbitrarily Q. And those letters are often paired together, which is great fun for our dyslexics, P and Q. What are we doing here? Like, what are we doing? And there was very little to support the suggestion that it stands for, pH stands for pondus hydrogeni, which would be quantity of hydrogen, or potentia hydrogeni, which is power of hydrogen. We kind of lean towards it being potential hydrogen, but we don't really know. So we've given P a whole new definition since he didn't bother to give us one, like come up with the term, but don't tell us what it means. So science has come up with a new one. It is decimal co-algorithm of, and then the number. Decimal co-algorithm of. And it's, yeah, that's P. And it's also used in the terms pKa for acid dissociation constants, and pOH, which is your hydroxide. So if you're measuring for the acidity or alkalinity of a solution, and you're measuring for hydrogen, you're measuring for pH. But if you're measuring for hydroxide, you're measuring for pOH. And P is decimal co-algorithm of. What is that? Okay, we're going to come back to what that means mathematically in a minute, okay? But pH and pOH. What do we get? What do we get? Oh, no commercials. Even better.
Our learning intention for this video is that we will understand pH and pOH and what they represent.
H, because she's an Aussie.
We can use
Yeah.
pH to tell us how acidic or how alkaline a substance is. If you've missed my previous video on revising acids and bases and the pH scale from Stage 5 Science, I'll link it up in the top right-hand corner of this video for you. The pH of a solution is actually a measure of the concentration of hydrogen ions that are in the solution. A solution that has a high number of hydrogen ions, we say is very acidic, and it will have a very low pH value. So a pH value that is less than 7 is said to be acidic. We can refer to pH as being the power of H, so power of hydrogen, or the potential of hydrogen. A solution with a high number of hydroxide ions, so that's our OH minus ions, is said to be basic and has a very high pH value, so something that is over 7, where 7 is neutral. We can calculate pH as it is defined as the negative logarithm of the hydrogen ion concentration of a solution. The pH scale is logarithmic, and as a result, each whole pH value below 7 is 10 times more acidic than the next higher value.
That's
So
true.
for example, a pH of 4 is 10 times more acidic than a pH of 5. And a pH of 4 is 100 times, so 10 times 10, more acidic than the pH of 6. And that is what we mean by logarithmic. Let me show you a couple of examples. We know that in pure water, the pH equals 7. But why does it equal 7? So in pure water, the concentration of the hydronium ion or the H plus ions are equal to that of the
Yeah.
hydroxide ions. And that concentration of each of those are equal to 10 to the power of -7. Now, if we substitute that into our logarithmic equation, so the minus log to the base 10 of whatever the hydrogen ion concentration is going to give us the pH. So if we sub this value in, then we get that the minus log equals 7. Now, if we do the same thing for the concentration of the hydroxide ions, we get the same value because we're subbing in the same concentration because the concentrations are the same. Now, this also makes sense because we know that the pH plus the POH is going to equal 14.
So there it was mathematically, right? And we'll come back to it again in a minute. I know some of you are like, woo! But basically you're doing factors of 10. It's logarithmic. So 10 times more acidic going this way, 10 times more basic going that way for every grade in the scale. So now we're going to play a little game. We're going to try and guess where these items belong. Are they acids or bases? So we'll start with milk. And we'll go by show of hands. Who says milk is an acid? Who says milk is a base? Most y'all are wrong. Oh, milk is acidic. All right. Wasp venom. Who says wasp venom is an acid? Who says it's a base? Now, this is interesting. Bee venom is an acid. Wasp venom is a base. Bee venom, if you get stung, throw some baking soda on it. Because it's an acid, it will help neutralize it. But wasp venom, put vinegar on it because it's a base. Oh, okay. Wasps. Yellow jackets are wasps. They are Satan's minions. I'm allergic to them. I don't like them. I have EpiPens now. Thank you.
My mom was mowing, her yard when she stepped in the yellow jacket.
Yeah, that's pretty awful. I stepped, well, I've had two terrible, okay. The second one wasn't funny. I was baking a cake and one had gotten in the house when I'd left the door open for a minute and I stepped on it with my left bare foot and it stung me in the soft part of my foot. And I ended up like with a huge reaction. That's what earned me my EpiPen. Like I didn't blow up, but my doctor's like, next time you're not going to be able to breathe if this keeps going. But I have permanent neuropathy in a spot about the size of a quarter on the bottom of my foot where all my nerves are dead. But the time before that was when I was working at cottage school and all the kids were in their classes and it had been a nice day. Doors had been open again. And another one of those Satan's minions got inside the building and I was going over to unlock the Coke machine or so I had to do something, take the money out of the Coke vending machine. I don't know. I went over to the Coke. I had on pantyhose, girls, pantyhose and heels and skirt. And I don't know what hair and I was messing with the Coke machine and it came and it landed on my leg. Now these will sting you and leave their stinger, right? They leave their stinger behind and then they go off to die. But wasps, yellow jackets will repeatedly sting you without losing. It's not barbed like a bee stinger.
They can sting after they die.
Well, let me tell you how many times they sting after they get stuck in the nylons of your pantyhose. It was just like, and it was like stinging the crap out of me. So I did the only thing I could do, which was skirt up, pantyhose down in the middle of the school. I'm like, I don't even care who sees it at this point. Like I was getting eaten alive by this thing. It was stinging my leg so badly that I stripped in front of the whole. Fortunately, they were in classes at the time. There was not class change, but yeah, I must have looked ridiculous because I ripping my pantyhose off, and it was still stuck in my pantyhose when I pulled them off. Like it was tangled in there. It was a mess. Like all those things, I hate them. Okay, bleach. Who votes acid? Who votes base? Most of you know. Next year we will use bleach to dissolve the flesh of a particular preserved specimen, and you'll get to take its skeleton home with you. Next year. Sorry. It's fun. It's a sea urchin, so you can do it yourself if you order one. You can get the urchin. Yep. Yep. It'll take all the spines off and it'll take all the guts out of the middle. It's great fun. All right. Mango. Who says acid? Who says base? Yeah, that's going to be an acid for sure. Vinegar's an easy one. Who says acid? Yeah, of course. You know that. Okay. How about lye? Don't know what lye is. What's lye? Yes, it used to be in soap. They used to put lye. They don't put it so much anymore, but yeah, lye used to go in soap. Yeah, it can burn you if it's too strong. So do we want to guess acid or base? Acid for lye? Base for lye. It's a base. Yeah, it's a very strong base. How about an apple? Acid? Base. It's acidic. Now, how about spinach? Acid? Base. Let me ask you this. Does spinach ever get kind of slimy? Oh, so that's a clue. Yeah, right. Spinach can get slimy. And anybody, when you eat spinach, do you get that weird, it's like a weird slimy film sometimes that comes with it. I had spinach salad last night. It was great. But sometimes cooked spinach is like, whoa. All right, pineapple, acid or base? Acid? Base? Yeah, that's an acid. Soda, like Coke, Sprite, acid or base? Acid? Base? Okay, here's the thing about soda. Even if you drink diet soda with no sugar in it, it can still put holes in your teeth because it's acidic enough that when it combines with saliva in your mouth, which is acidic, you get even more acid and then it can eat away at your enamel. So even your diet sodas, yes.
Put tarnished penny into a cup of Coke, it will clean the tarnish.
Yes, it will. Coke does all. I've seen people clean battery terminals with Coke in a car. Yeah.
Still drink Coke Zero.
Yes, but it still has acid. It'll still get you. Yep. Even if there's no sugar. Like that's my favorite. Actually, I just tried this. I just finished it. I just tried this orange cream Coke Zero. It wasn't terrible. Yeah.
Of Mountain Dew, like melting some rat in his head.
Yeah.
Yeah.
Could be, man. I don't know. I wouldn't be surprised.
Yeah.
Anybody on Instagram follow Pookie and Jet? You know who Pookie and Jet are? I think they're right above where you guys are caring about, but they have a hugely popular Instagram channel. They're from Atlanta. It's Campbell Hunt Puckett is her handle. But they're like a super rich yuppie couple that travels everywhere and cares about fashion. If you want to laugh, but that's what made me try this is Pookie was drinking it and I was like, oh, okay, I'll show Pookie. He sells dental practices, which apparently makes good money because they are very wealthy. But they're kind of awkward and weird, but they're interesting. Like he buys her the most expensive clothes. They just had a baby. Here's an example. They just had a baby. She got a push present, which is what sometimes daddies give to mommies when they have a baby. Oh, here's a gift for you. Usually it's like, you know, a little piece of jewelry or some flowers. He bought her like a $30,000 bag. Not kidding. But this is what they do. She comes out and he goes, Pookie is fire. What are you wearing, Pookie? And she's like, I'm wearing, and then she goes through like her whole outfit. They're funny as heck. I'm telling you, it's hilarious. They take themselves seriously, but they're funny. So anyway, that's why I'm drinking, because Pookie drank it. I'm like, all right, influencer, you influenced me. I'll try it. All right, so hand soap. Who says it's an acid? And who says it's a base? A lot of soaps are going to fall in the base category. All right, lime, as in a lime, the green thing you put in your soda, acid or base? Acid? Yeah, that's an easy one. Baking soda, you all know this, acid or base? Base. Window cleaner, if you're talking about the kind with ammonia in it, is gonna be what? Base, yeah. Now you can clean your windows with vinegar too, which is an acid, but if you buy, yeah, stomach juice. It's technically called stomach juice, which is really gross. It is hydrochloric acid. You're all right. And how about drain cleaner? Anybody want to guess? Base. Question. What is the typical chemical in that? They're talking about like drain cleaners that have a strong base in them. Do you know what that base is?
Yeah.
And what did you use in lab today? Sodium hydroxide. It is far more concentrated, less dilute sodium hydroxide. That's what you find. The same stuff you used in lab today is the stuff that you will find in your drain cleaner. Fun. So what do we calculate pH from? Somebody said it earlier. Yeah, from your hydronium, right? All right, so hang on, there's a lot of side chatter. Okay, from your hydronium. So here's how you do it. Here's that log again, the whole logarithm thing. So pH is the negative log hydronium. So what does log mean? Okay, we'll go over it again. A logarithm is the power to which a number must be raised in order to get some other number. So for example, the base 10 logarithm of 100 is 2 because 10 is raised to the power of 2 gives you 100, right? 10 raised to the power of 2 gives you the number 100. So log 100 equals 2 because 10 to the second power is 100. Do we all agree with that?
Yeah.
So what would log of 1000 be? 3. There you go. Right? Yes.
Also, there's no, you're supposed to add a subscript to log if it's not a 10.
Yes, you can add a subscript to log if it's not a 10. Yes. But the assumption for log is that, boys, the assumption for log is that it's 10 unless you add a subscript. So this is an example of a base 10 logarithm, which we call it base 10 because 10 is the number that is raised to a power. The base unit is the number being raised to the power. There are logarithms using different base units. If you want, you could use 2 as a base unit. For instance, the base 2 logarithm of 8 is 3 because 2 raised to the power of 3 equals 8, which looks like that. Do we agree? Do you see, as he just said, as Yusuf just pointed out, the subscript? If there's no subscript, it's 10. Okay, that's just the assumption. If there is a subscript, it's telling you that you're raising it to a different power. So in general, you write log followed by a base number as a subscript. The most common logarithms are base 10 and natural logarithms, and they have special notations. In base 10, log is just written. That's what we said, just log, right? Log. All right, so how do you put this in a calculator? This is actually easy. Do what?
So like X, Y.
Yeah, sort of. So look, if you wanted to do your pH is negative log of hydronium, what is the pH of a solution with the following hydronium ion, Gabe, concentration? So if this is your concentration, 2.4 times 10 to the negative 10, this is your concentration of hydronium ions. What would you do? It's so easy. So here's what you do. pH is the negative log of hydronium, right? So pH is the negative log of this number because this is our hydronium concentration. Do we see how everybody sees that, right? So how do we do it? First, you enter this into your calculator and hit the EE or exponent key. So we put it in, we hit EE, and then equals. Boom. Next, you hit the log key and take the opposite sign. So your pH is 9.62. That's it. That's all you had to do. So if you want to watch it again, yeah, there you go. Put in your 2.4 exponent 10. And then there's your 10. And there you go. Boom. hit the equals key, take the opposite sign. So you have H plus and OH negative, and your H plus is your concentration of hydrogen ions at your pH. Your OH is your concentration of hydroxide ions at your pOH. Look at your pH scale here and your pOH scale here. What do you notice about them? Bless you.
They're opposite.
They're opposite, right? You're measuring pOH. This is pH, bless you. They're basically mirror images of each other, right? Okay, notice something. Toothpaste is basic. Toothpaste does not occur in nature. We created it that way for a reason. Why is it basic?
So we don't.
What do you think, Asher?
Don't put any holes in our teeth.
Oh, but look though, it's 10. And that's what, 3 away from 7, but we drink coffee, we can drink vinegar. That's 4 away from 7, so vinegar doesn't, do you have another thought, Hayden?
Is toothpaste basic so we can neutralize the acids?
Where's the acid coming from?
I was like,
Sodas and anything else that you might drink. Or...
Yes, yeah, everything, but especially, yeah, your saliva. Your saliva is acidic. Remember earlier I said saliva is acidic?
Yeah.
Your saliva is acidic. Now here's the fun thing. Some people just genetically make more acidic saliva. Anybody ever take like really good care of your teeth and still get cavities? That's me. and the dentist finally looked at me and said, I'm sorry, you just make really acidic saliva. I'm like, that's fun. Thanks so much. So like, they barely ever need to clean my teeth because I'm so fastidious about it because I've had too many freaking cavities and I hate them. I hate getting drilled. So anybody here have the redhead gene? Do you know what I mean by that? Caitlin, you might. You've got a little strawberry blonde going. So I was born with flame red hair. It's darkened as I got older, but I definitely have that gene. There's a gene that redheads have that make you resistant to anesthesia. You know right?
But
Have you got it? Your mom has redder hair, so yeah. So it's a weird thing. And finally now, like anesthesiologists and dentists and stuff are really listening. So my new dentist that I had to get my dentist retired, and my new dentist, the first time she's like, well, you got 2 cavities. I'm like, shocker. Every time I come, I'm not going to have this thing left to drill sooner or later because it just doesn't matter what I do. And I said to her, I said, look, before she started, I said, I'm one of these people. Every time you start, I've never been through a drilling where I didn't have to raise my hand because I could feel it. Like, there it is, wore off, because we metabolize the anesthetic too fast, faster than most. So she was like, oh, it's real. She was the first person to believe me. She's like, it's real. I hit you hard. Dude, half of my face, my eyelid was numb for 8 hours. It was so, all day. Eyelid, I'm walking around like, but it worked. And it's the only time I haven't had to get hit multiple times. So yes, good for her. So yeah. So anyway, back to the teeth thing. So yes, we do have more basic toothpaste intentionally to help neutralize the acid that naturally forms in your mouth. But like, you can eat, see, vinegar you could straight eat, like if you have deviled eggs or pickles or whatever, here's vinegar. So it's down here, it's pretty acidic. You can tolerate that in your mouth. Now, vomit in your mouth is not so nice. And vomit in your throat is not so nice. But in your stomach, that stomach acid is fine in there, right? Because what? Yeah, there's lots of different mechanisms that go on that make it so that your stomach can maintain gastric juices. There's that word again. You said stomach juice. There it is. Gastric juices is what they're called. And maintain that stomach acid without it eating through your stomach.
What's that weird taste in your mouth? Like, is that acid reflux when you have a weird taste in your mouth?
Can be. It can be. Depends. It depends. But yeah, reflux is heartburn, right? Like you get some of your gastric juices make their way up into your esophagus. And it can really burn and it's terrible. That's why Tums are for, because Tums are calcium carbonate, which is a base. So it automatically neutralizes. So one of the meds I used to take caused like really awful heartburn and it didn't always do it. Sometimes it didn't, sometimes it did. But I woke up one night in the middle of the night and it was the most pain I'd ever been in from something like that. I even questioned if I was having a heart attack. Like it was so bad. And I was eating Tums by the handful. It was making no difference. So I had to force myself to drink water with baking soda in it, which was gross, but it stopped it. It was the only thing that stopped it, because you have to neutralize it. Again, it's neutralizing. So indicators. So we used indicators today in lab. What's an indicator, Caitlin?
It's a combat reversibly. Yeah, that thing.
That thing, yeah. So it gives a visible sign, usually by a color change. Oh, that's just spelled the British way. Of the presence or absence, I don't think I meant that, of a threshold concentration of chemical species such as an acid or an alkali in solution. And then we also have pH meters, which can read your pH. And that's an instrument that they use. I have water testers that we use sometimes in lab, and they can check for pH as well as conductivity and things like that. There are two different methods that are primarily used for people with acid reflux to see how much they're refluxing. So they can do what's called a pH probe, which is like a little, it's like a little tube, right? And they thread it down your nose and tape it to your face so it doesn't move. And it sits in your esophagus and it just kind of hangs in there, but it measures the height and frequency of gastric juices coming up into your esophagus. Came up this high, came up this often. So it's checking for that change in pH, and it records it to like a little device that you just wear, like a little bag that you keep in your, like a little sling over your shoulder. And you wear it for like 24 hours. And then you go and they take the tape off your face and they grab it and go, and they whip it out of your nose real fast, and doesn't hurt, but it's not comfortable. That's what they use on a lot of people, but primarily children, because the other option they have nowadays is called a Bravo cap, but you have to be over a certain weight limit or you will feel it. It looks like a pill, it's tiny, but it has little barbs on it. So they'll do an endoscopy on you and they'll go down in there with their camera and they'll bang, shoot it into this wall of your esophagus, and it goes, and it just grips on and it just hangs there, and it measures how often you reflux. And they don't go in and remove it. It falls off on its own, makes its way out, and you never even see it again. It just goes away. You flush it away and it's gone. You don't even know that it's gone. Yep. So those are two different kinds of pH meters that are used medically. So here's our favorite Professor Dave. We love him. Oh, he's working. He's working. Look.
Oh, it's a boy. And it looks like he's gonna like Westerns.
What?
Okay, I don't even know what that is.
Today, let's talk about acids and bases. We've probably all heard the terms acid and base, but what do these words mean on the molecular level? Let's discuss the rigid definition according to a few different models. Most often, when we talk about acids and bases, we are referring to the Bronsted-Lowry definition. According to this model, an acid is something that donates a proton, and a base is something that accepts a proton. An H+ ion is a proton because if a hydrogen atom loses an electron, all that is left is the proton that comprises the nucleus. Proton transfer is a big part of chemistry. An acid and base will react to form a conjugate acid-base pair. The thing that gives up a proton is the acid, the thing that accepts it is the base, and on the product side, the base has become the conjugate acid, and the acid has become the conjugate base, because the thing that gained the proton could potentially lose it again, acting as an acid, and the thing that lost the proton might gain it back, acting as a base. The Bronsted-Lowry definition only applies to protic species, or molecules with hydrogen atoms that can be lost as protons. But there are aprotic species that also display acidity.
Well, now we're going to
basicity.
complicate it more.
This is what the Lewis definition entails. Under the Lewis definition, a base is something that donates a pair of electrons, and an acid is something that accepts electrons. A Lewis base is indistinguishable from a Bronsted-Lowry base, but the acids differ in the sense that a Bronsted-Lowry acid must have at least one hydrogen atom. A Lewis acid just needs some partially positive atom. A species that can act as both a Bronsted-Lowry acid and base is said to be amphoteric. Water is amphoteric because it can behave as an acid, losing a proton to become hydroxide, or it can act as a base, gaining a proton to become a hydronium ion. In a sample of water, a tiny fraction of molecules transfer a proton from one to another, which we call an acid-base reaction. This is an equilibrium and is shown here. We can write an equilibrium expression by showing the concentrations of the products over the concentrations of the reactants. We will only include gases and aqueous substances, so here it will look like this. At room temperature, this equals 1 × 10 to the -14, or 1/100 trillionth. That's the fraction of water molecules that are ionized at any moment. As temperature increases, Kw increases. Hydronium concentration, which is essentially proton concentration, if above 1 × 10 to the -7, gives an acidic solution. If below, it's basic. If equal, it's neutral. When looking at conjugate acid-base pairs, we must understand that a strong acid is something that will very readily lose a proton. If something is a strong acid, it means its conjugate base is very stable. That's why it's so willing to lose a proton. A strong acid will have a weak conjugate base, since the conjugate base will be very stable, meaning it isn't dying to pick up a proton. A weak acid, something that isn't very willing to lose a proton, will have a strong conjugate base, something that will very easily gain a proton. So if the strength of an acid is proportional to the stability of the conjugate base, we have to be able to predict the stability of conjugate bases in order to tell how strong an acid will be. Whichever atom is losing a proton, the larger it is, the more stable the conjugate base will be. Comparing the acids made by combining a hydrogen with a halogen, we can see that Hi is the strongest. This is because when the proton leaves, we are left with an iodide ion. This is much larger than a fluoride ion and therefore can diffuse the negative charge around a greater volume, thereby stabilizing itself. Fluoride is much smaller with a very localized charge and is therefore less stable. So hydrofluoric acid is a much weaker acid than hydroiodic. Also, the more electronegative an atom, the better it is at accommodating a negative charge. So an oxygen atom can more readily lose a proton than a carbon atom, which is why something like water is far more acidic than, say, methane. Acids are also stronger when their conjugate bases are resonance stabilized.
Oh, we get a midway commercial. Hey,
A carboxylic acid is about 1 trillion times stronger an acid than water, even though both of them leave an oxyanion after deprotonating. This is because the conjugate base of the carboxylic acid can share the burden of the negative charge between two oxygen atoms by resonance, while hydroxide can't. These resonance structures don't actually exist, but rather the composite resonance structure does, which shows delocalized pi electron density distributed about this portion of the molecule. More on this in organic chemistry.
yeah, we're not doing that.
There can be
That's a lot.
monoprotic acids, which can only lose one proton, or polyprotic acids, which can lose several. Polyprotic acids become less acidic with each deprotonation. In an acid-base equilibrium, the side with the weaker acid-base pair will always be favored. This is because the stronger acid or base will have a greater tendency to react and generate the weaker species. We can tell acid strength by looking at an acid's pKa. The lower the pKa, the stronger the acid. Strong acids deprotonate completely, transferring every acidic proton to molecules of solvent or other things in solution. Weak acids only deprotonate partially, generating some of the conjugate acid, but won't react completely. The weaker they are, the less completely they will react. Once again, the hydronium concentration measures the degree to which an acid transfers protons to water molecules, and therefore the strength of the acid. But hydronium concentrations have inconvenient exponents, which can be cumbersome to list.
Inconvenient.
So we have developed a more convenient way to describe acidity. The pH of a solution is the negative log of the hydronium concentration. Logarithms are the inverse operations of exponents. So the reason why a negative log is useful here is that it takes an annoying number like 10 to the negative 7, and it turns it into 7, which is much tidier. So a solution with a pH of 7 has a hydronium concentration that is considered neutral. We can also measure the basicity of a solution by calculating the pOH. This is because a strong base will generate hydroxide ions in aqueous solution by stealing protons from water molecules. Just like pH, pOH is the negative log of the hydroxide concentration. Another way to calculate pH and pOH is by using the formula for Kw. From this, we see that pH plus pOH must equal 14. Between these relationships, we can relate pH, pOH, hydronium concentration, and hydroxide concentration, and we should be able to get from one to any of the others using this chart. Let's check comprehension.
Got it, we got it. All right, so here's your problems from your binder work. Could a Bronsted-Lowry acid not be an Arrhenius acid? So for instance, in a gaseous phase, hydrochloric acid donates a proton to, what's this again? Ammonia, right? For NH4Cl. This reaction does not involve the production of hydronium ions. So hydrochloric acid is not acting as an Arrhenius acid in this case. Can a pH be negative? What do we think? No. No. pH is negative whenever the hydronium concentration exceeds 1.0 molar, but that's really a rare, you're not gonna see it. Is the list the observable properties of each. So observable properties of acids. Give me some, Caitlin, Jordan. In the presence of a base, it might.
Really observable, but tastes sour.
Tastes sour, that's observable, that's an observation. So yeah, sour, burns the nose sometimes, Andrew. Sticky, reacts with metals, reacts with indicators. How about a base? You got bases?
Bitter.
Asher?
They can also.
Yeah, they can burn things too. Bitter, usually no smells. Slippery, react with oils and fats, indicators. All right, before I show you the last one, do you want to hear a funny story? Or do you not care? You want to hear a funny story? Okay, I've told this story. Drew's heard this now 5 times, but this was the funniest thing that's ever happened to me, at least in the last year. So we were in Fort Worth over the weekend, right? For a gymnastics meet. And we left Sunday afternoon. And we got a first class upgrade. So we gave it to Drew. And so Jason and I sat coach and we gave Drew the first class. So Drew was already on the plane, sitting there with his, champagne. I don't know. While we were in the line like little peons. And my husband's a million miler. Okay. He travels all the time. He's got a little glass trophy from Delta that says million miler. We're like, special. Okay. So he's like, I'm incognito with all the regular people. So we're standing in the line. Okay. And there's a man ahead of us. Now, if you've been flying recently, you know that all you need to do is take your phone and go, or the lady goes, and that's your boarding pass, right? This is not hard to do. This man in front of us is standing there, and it's now his turn. He's FaceTiming with somebody, so he's not paying attention. And so she's like, boarding pass. So he's like, oh. So he's like trying to get his phone. We're like, I'm sitting there like, come on, you're waiting on him, He's like, what does my husband call them all? I forget. I don't know. Anyway. Huh? Yeah, that would be good. But anyway, just ridiculous, just ridiculous. So we're waiting on him. And he finally gets it out and hands it to the lady, and she's trying to scan it. And this lady, this is this middle-aged lady in her little Delta dress with her little scarf, right? And she's, there's those ropes that they use to separate things, and you pull them out and you let them go and they zip back, right? So we're standing there and she goes, let me see it. So he hands her his phone. Not kidding. She went, ew, that's Spirit Airlines. This is Delta. With the rope down the hall. Spirit has not a great reputation. Ew, that's Spirit. This is Delta. Down the hall. So he goes, okay, and walks out of the line all stiff-legged and confused like this. And if that wasn't funny enough, She pulled the rope back, stuck it back in, and then looked at my husband and said, I am so sorry. In tears, like I'm laughing so hard because my husband's looking at me going, so sorry you had to see that. You know, that's what it was. Her reaction was like, I'm so sorry you had to see this man in our lives. Spirit Airlines. Down the hall. Get out of here. It was so deadpan. Oh, Spirit, this is Delta. Down the hall. Like just as deadpan. She was serious. All right, so for your last one. Sorry, so you can think of, the more you think about it, the funnier it gets. So anyway, so sorry. Anyway, so if you're gonna calculate the hydroxide ion concentration in aqueous solution that has hydronium, so if we're calculating for hydroxide ion, for hydronium, we're looking for POH. So what you would get is you do 1.0 times 10 to the 14. This is the whole formula. That's how it breaks down. And they're inversely proportional. I'm not going to make you do like tons of these on tests or things, so don't panic about them, but understand that it's a process and you should kind of know how it rolls. So, and there's the rest of it. Sorry, I thought I had clicked it. There's the actual answer. Sorry, we were getting there. So yes, if you work out all the math and go all the way through, that's the answer you would get. So if anybody attempted that in your binder work, there you go. So next week is our last Q3. Last Q3 lesson. And then we're in Q4. Everybody's got their Q4 packets. So, you know, get them in your binder. Don't lose them. And, oh my gosh, so funny. And so, what are we all doing this for? What are you afraid of? Oh, being on a separate team. I still got to do that. Find that out soon. So if you know, go ahead and make sure your lab is done. Bring it back next week. Right? And be sure that you use that group data and you're good to go. Here you go. I'll put these up here for you. There you go. Have a good week. Random jawbones in here. I love it. Yes, sir. So that's a good question. I wanted to know what the parents thought, and I got just a little bit of feedback. Are you wanting it?
If you are gonna do one, I'll go.
Okay, I will do it then. I was waiting to see if there's, hey guys, Liam asked a good question. Who here is interested in another spring dance? Okay, so a couple of you are. I like hosting them, but the problem is last year we had some people that were completely ridiculous and like poured soap all over the bathroom that we had to stay after and clean up. It was not cool. So it's the first year that we had any behavior issues. As long as we don't have behavior issues, I'm good.